In the previous class we have discussed how to use a resistance sensor for current transmitters. So, there we have discussed how to design a 420 milliampere current transmitter per pattern resistance thermometer. Now, these current transmitters are very popular in the process control industry, and there are two types of current transmitters, that is, one is this 420 milliampere 2-wire based current transmitter, other one is 3-wire current transmitter where 0 to 20 milliampere is used. So, let us familiarize how to design a circuit which is suitable for 3-wire system. So, so we will discuss about 3-wire current transmitter in this class. Essentially, we should first understand what is the difference between 2-wire current transmitters and 3-wire current transmitters. Now, in 2-wire current transmitters we had a source, and then the 2 wires were running, and then we had the current transmitter is here, and then that is linked to, for example, it is a potentiometer based, then we have a potentiometer is connected to the system, and then we have 0 adjustment and span adjustment is provided like this, and then the current through this is actually 4 to 20 milliampere. So, the current will be 4 milliampere when the potentiometer is at one end, and when the potentiometer is at when this potentiometer is at one end, then current will be 4 milliampere in this, and when the potentiometer is the other extreme, the current will be 20 milliampere, and that adjustment is done using this 0 and span adjust parts. So, keep it at one end and adjust the current for 4 milliampere, keep it at the other end, adjust the span for 20 milliampere. This is repeatedly done few times, such that potentiometer is at one end you get 4 milliampere, other end 20 milliampere, and then the measurement is carried out by adding a resistance here. So, voltage across this gives you the current information, that indirectly gives you the position information of this potentiometer. So, this voltage measurement is utilized for taking the data out essentially. So, this resistance will be up to 600 ohms, and the typical value is 24 volt. This is actually called 2-wire current transmitters, because we are using only 2 wires which carries both the power and then carries back the signal as well, and this is quite popular, but the accuracy achievable in this is about only 1%, because this current whatever is flowing here that should get affected only by this, and this temperature change etc. of this circuit should not contribute any current for in this circuit, but eventually this temperature drift used to contribute some amount of current change here. So, that puts a ultimate accuracy limit for this circuit. So, to get high accuracy we need to go for 3-wire system, that is what we are planning to discuss in this lecture. So, 3-wire system looks like this. So, this is called 3-wire current transmitters. Three-wire current transmitters essentially looks like this, that you have potentiometer, the voltage source, and then it is given to the system, the 3-wire current transmitter. So, this is then one more wire comes out and that carries the current back to the system, and whatever measurement you want you put a resistance and measure. That is, this is one wire, this is second wire, this is third wire, this is current transmitter. Of course, the parameter which is to be measured, for example, is the potentiometer, then it is connected like this. So, this is the model of a 3-wire current transmitter. In this signal is now coming in this terminal, the third terminal, and that current is converted into voltage by adding a resistance here, and this also typically around 600 ohms, and this also 24 volt. Of course, this also has the 2.70 and span adjusting potentiometers are there. For example, we have here 0 pot and then span pot. So, normally what is done is that you keep the potentiometer at one end and adjust the 0 to get 0 milliampere in this, then take it to the other extreme and adjust the span to get 20 milliampere in this line. So, this is done repeatedly 3-4 times, one end for 0 milliampere, at other end 20 milliampere, that is adjusted using 0 and span pot. So, eventually when this is moved, at one end you will get 0 milliampere here in this wire, and at the other end you will get 20 milliampere here. So, this is actually 0 to 20 milliampere current transmitter. So, unlike there in two-wire system we have 4 and 20, here we have 0 and 20. This is because the current consumed by the circuit is not coming in this signal wire, because even if the current consumed by the circuit changes, it has no effect on the signal. So, even if the current consumed by the circuit changes, you will have no error on the measured quantity. That is the advantage of 3-wire current transmitters. 3-wire current transmitters are more accurate than 2-wire current transmitters because of this elimination of this current, this varying current problem, because the circuit current about the circuit current one need not worry in this case. So, this 3-wire current transmitters also popular. Let us see how to design this 3-wire current transmitters. So, 3-wire current transmitters are made for 0 and 20 milliampere. So, one end it will be 0 milliampere, other end it 20 milliampere. So, we call it is 0 to 20 milliampere current transmitters. Now, the design of the circuit is slightly easier compared to the 2-wire system. For example, the power supply what is required can be easily designed without worrying about the current consumed by the power supply. For example, in 2-wire, 3-wire system we can have a input power supply design. One can use a conventional power supply itself, and the power input to this can be directly from the supply itself. One need not struggle like what you had in the earlier case. You know, the power supposed to be from the regulated voltage, because the even if the input voltage changes, okay, this has to be changed to a DC supply. So, a DC supply. So, one gets a DC supply straight away, and even if this voltage changes, the current obviously the current will change, but that current is no more issue, because we are not measuring current flowing through this in a 3-wire system. So, the design of this become slightly easier. Now, what normally done is that you can have but still this zener is required to start the voltage regulation process. So, this we already discussed in the earlier lecture, what is the function of this zener, and then at the output we can have the voltage divider. And then the reference zener can be put here. This is one possible regulator design. but this need not be the only circuit, because it is a 3-wire system. Even the conventional voltage regulator chip can be used for this purpose. All that required is one has to get a steady voltage across these 2 points. Of course, we need to have a capacitor, and this capacitor also can be electrolytic, no harm, because even the leakage that develops is not a serious issue. So one can have the regulated voltage, and this can be even the conventional regulator. So all that needed to be done is you get for example the required regulated voltage, and this has to be slightly higher. For example, if it is a 24-volt supply, and if it is having plus or minus 10% variation, then the voltage can be even kept at 18 or 19 volt regulated voltage, because we need to drive 600 ohms 20 milliampere later in the current transmitter. So we need to have this kind of voltage at this point. So we will not discuss much about the voltage regulator part, which we had already done in the earlier case. So and this regulator design is not a critical issue in the 3-wire system. So we assume that we have a regulated voltage of 18 volt coming to the circuit. So next step would be we have to go for 3-wire current transmitter circuit design. So the current transmitter part we have to design now. If you look at the current transmitter design, now one easiest thing, there are two possible circuit topology can be used, and one could be this. The current transmitter of this type, and then we can have a for example in this case, if I have a voltage here, then you have a current that is coming here. So now the current actually flowing through this is given by this Vz, and this is supply voltage, say that plus 18 volt, assume that is what we got it in the other case. So this is 0 and 18 volt, and if this is R, then I actually will be equal to Vz by R. So in this case, if I can use this model for 3-wire system. In this case, the third wire will be this one, that is, instead of putting this resistance here, what you do is we will give this as output terminal, third wire. So we have in this model we will have a voltage regulator coming here, and this is 24 volt. This is a voltage regulator. This is 24 volt, which we this voltage that we have discussed, and then this is acting as a first wire, this is acting as second wire, and then this is acting as a third wire, and the user can connect a resistance here at the receiving end, and then see the current. This is one possible model we can use for current transmitter. This has disadvantage, mainly because we have to generate the variable voltage. When the current is to be varied, then this voltage has to be varied, then only the current can be varied. So in the case of potentiometer based system, then one can do this. For example, I can have I can add the potentiometer here across this, then connect the potentiometer like this. For example, if a potentiometer change supposed to produce a current change here, then this model can be employed. When the potentiometer is at one end, then you will have 0 milliampere current, because this voltage and this voltage will be at the same potential. For example, if this is going and sitting here, then this is going and sitting here, then you will have for example, if this is 18 volt and if this is also sitting at 18 volt, then no voltage difference and current will be 0. So, you will have a 0 current, and when the potentiometer comes to other end, then if this is 18, if this is says 1.2 volt zener per use, then it will be 1.2 volt, then 1.2 divided by the resistance will be the current. One can adjust this voltage and this resistance to get the required current for this moment. So, when it is at one end we can have 0 milliampere, when this potentiometer at the other extreme we can make it 20 milliampere. It is quite possible to scale this resistance and this zener correct it to get 420 milliampere, but this has one drawback, namely that if the supply is 18 and we know that we have to give power supply for this also to be made 18, that if this power supply also 18, then it will not work up to 18 volt, because supply itself 18 and this calls for little less than 18, this also calls for little less than 18. But if this is supplied directly from 24 volt like this, for example, I can have this power supply connected ground here, and then this directly connected to the input, then this circuit works well, and then one can get 0 to 20 milliampere in the 3 wire system, because this supply then supply for this is definitely more than this, and in that case we will have 0 to 20 milliampere coming properly without any problem. But there is one drawback of connecting this directly to the mains, that is, if whatever noise that is present here, that is directly coming to this without any regulation, and the output also, this noise voltage influences the output current, and the output current also will have noise. So, normally this is not preferred circuit. So, one can modify this slightly to get the to get rid of this regulation, the noise problem. So, normally what is done is that instead of connecting it here, we can connect it in a slightly different way. We can see in the next circuit. What we can do is we can have a regulator that can be in the conventional form what we had discussed earlier. So, we have a regulator, voltage regulator. So, we have the input voltage coming to this and the regulated output coming in. So, we feed the regulated supply only to the, this is ground, and the regulated supply only we feed to this, then we connect similar to what we have discussed, the current transmitter part. Then this regulated output only we connect to the potentiometer. Of course, to limit the voltage across that, we can have this zener. Even if the regulated voltage, even the zener is not required, one can scale directly, even without zener also it works already, there is no problem. So, one can have this directly connected here, and then one can have this potentiometer connected like this. Then only issue would be we had that this and this when 0 current is there, this voltage at this point will be equal to voltage at this point, and the supply also at same potential, that is this and this, as for example in the earlier case we have connected all these three together, and 2 wire system, 3 wire system we will have this going out separately, then it is connected back. So, in this case our original issue was that the supply of this is same as this potential, no current is there, there is no voltage drop at 0 current. So, this also goes up to the supply voltage, and the potentiometer is moved to one end, and this end also goes to the supply voltage. and op-amp input will not accept exactly the equal to the supply voltage. The input has to be little lower than the supply voltage. So this was the problem that we had discussed in the previous circuit. Now we can modify this to get rid of that problem. What normally done is you remove this and this supply to this, you can give to directly to this, and these two can be powered using a slightly lower 2 diode drop less than what is actually at this point, and then to make this point stable we can have one capacitor and a very small current can go in this to make sure that the diodes are biased and some 1.2 volt drop is there. So now 1.2 volt reduction in voltage is achieved by this arrangement. So the earlier issue of the inputs going up to the supply voltage terminal is resolved by adding these two diodes. But still we have to add, now we have to add 0 and span adjusting potentiometers to this circuit, then only it will be commercially viable circuit. This is because this is the part that actually controls the 0 and 20 milliampere. When at one end it will be 0 milliampere, at the other end it will be 20 milliampere. Unfortunately what happens, this part will be mechanically linked. Normally this part is mechanically linked to the system whose position to be measured. But this when they connect mechanically, when the wiper moves to one end, it may not reach, potentiometer may not reach the end of the physical end of the potentiometer. So mechanically the system might have moved to one end, but the potentiometer might not have moved to the one end. Similarly, the potentiometer might not have moved to the other end when the system is driven to the other extreme. This happens because of mechanical misalignment. So one have to take care of that. That is, I should get, even if this is not reaching the one end of the potentiometer, current should be 0 milliampere, and the achieving that is a tricky issue. So that we had, and then similarly when other end is there and the current, the voltage may not have reached a full value, the potentiometer may stop little away from the end of the potentiometer. For example, if this is 5K pot, if this is 5K pot, if I take this as my one end of the point, then when the potentiometer is moved to this end, then if I try to see the voltage resistance between this point and this point, that is the resistance between this point and this point, or voltage across this, when the potentiometer moved to the one extreme, this extreme, I should get 0 volt. That may not be exactly 0. Similarly, if I had designed around 2 volt across this, then when the potentiometer moved to this extreme, I should get 2 volt across this. You may not get 2 volt, you may get only less than 2 volt. So this problem to be handled, and for that we have to provide 0 and span adjustment. Now one can do that. For example, if I want 20 milliampere, I can have 2 volt drop across this. I can have a 2 volt drop across this. Now that I can exactly achieve this by putting a for example, I can have 2.4 volts inner here. So one will get 2.4 volt across this. Only thing is that it may not go when it goes to one end. For example, if this is if you write the values that it is 18 volt and this is expected to get 1.2 volt drop, we may get 16.8 volt, and this will be 16.8 volt and 2.4 volt. Each one is 1.2 volt diode, Zener diode. So 2.4 down, so 16.8 minus 2.4 will give you 14.4 volt. So one suppose when the potentiometer is moved to this extreme end, when the potentiometer is moved to this extreme end, the voltage should be 14.4. When the potentiometer is moved to this extreme end, it is supposed to 16.8, which may not happen because of the physical limitation. So, we have to deal with this by adding 0 and span pot. For example, if I want 20 milliampere, then in this case we have to fix this value. So, I will fix this resistance R. So, 2.4 volt supposed to give me 20 milliampere. So, total voltage change, total expected voltage change, is 2.4 volt. It will be definitely less than 2.4. So, we can take normally 20% both sides going off. So, real voltage change, real expected voltage change. That is, we theoretically we expect 2.4 volt change here. When this point is moved across this, we expect 2.4 volt change, but in reality it may not be 2.4 volt. On both sides normally expected to have about 20% error, that is mechanically not able to move very close to the end. So, if I take 20% change, that means each point I can leave 0.4 volt, that means I can have only 1.6 volt change is only expected in real life. So, we may expect only 1.6 volt change. In that case, for 1.6 volt change should give me a current of 20 milliampere. So, current change of 20 milliampere, because this voltage, the voltage change here, this voltage change divided by this resistance is the current, which you have discussed in the earlier circuit design. So, the current change, the expected real current change for 20 milliampere expected real current change, expected current change, required resistance values. Required resistance change, required resistance is actually 1.6 divided by R, that is supposed to be equal to 20 milliampere. So, that comes, R works out to be 1.6 divided by 20 milliamps. That comes out to be thousands. You will have 80 ohms resistance is what is actually required to get that change. So, if I put 80 ohms here, then if 1.6 volt change occurs, then I will have 16 milliampere current, but we know that some potentiometer can go more than 1.6 also, but none will, we assume none will go below 1.6. So, when some potentiometer go to the extreme end, then the current can go higher. So, we have to solve that issue. So, we have to have a variable resistance R. So, normally the variable resistance part is achieved in the following manner. So, what is done is, if I look at the current transmitter part alone, it will be like this. We can have, and this is the that 1.2 volt Zener and the potentiometer to go with that. And our 3-wire resistance is coming here. So, normally what is done is, we add a potentiometer here and then terminate this with another potentiometer like this. So, this is taken as a span pot. So, For example, when this is we take it as a span potentiometer. And of course, we also have to add a Darlington here to make sure that the current actually whatever that current is flowing, the same current is flowing here, and we want to make this base current negligible, then only the current that is coming here is same as this, because we are sensing this current and this current is taken as output current. So, whatever current that is flowing into the IC will be lost. So, we have to make sure that this base current is negligible. So, we normally add a Darlington to this. So, we can add a Darlington to this. Can add a Darlington to this. That will make base current negligible, and this will get the span will get adjusted with this. Now, that adjustment to be if it have to happen properly, then one have to calculate the values correctly. So, normally what is done is that we will have resistance here. For example, we need 80 ohms resistance here. If 80 ohm is put, when the potentiometer comes to one end, then when it's 1.6 volt is there, when the here if this point is less by 1.6, then if it is at this extreme, then you will have exactly 20 milliampere flowing, but sometimes this difference can go even more. So, if it goes more, say for example 2 volt, then 2 volt by when this is at the other end, then 2 volt by 80 ohm will give more than 20 milliampere. And if you want to reduce, then you have no way of reducing. So, normally what is done is that we can have this resistance little higher, so that you have some adjustability. So, for example, I can have 100 ohm resistance here. So, when at one point when the voltage here, this point is compared to this point, if it is less by 1.6, then one can always move this upward to make it equal. So, now if we can adjust this and get 1.6 get 20 milliampere, even more than 1.6 volt. For example, in the case 1, we take for case 1, if this is for example, if this is 16.8 volt, and if this is sitting at 14 point in our earlier case we have designed this one 14.4 volt. This 14.4, then we got exactly exactly 2.4 volt difference. So, 2.4 volt difference, if the potentiometer is at this extreme, the span at the extreme, then you have a current of 2.4 volt will be 100 ohm, which will be 24 milliampere, which is actually coming higher. Now, to reduce the current, what we can do is we can move the part little closer, or need not go up to the end. We can go here and keep it per with 100 ohm we need only 20 milliampere. So, one can move this away such that the voltage difference is only reduced, because this voltage and this voltage try to reach the same point. So, one can adjust this potentiometer and this resistance such that whatever combination we want we can achieve. So, one can have this span adjustment such that when it mechanical end of the when the potentiometer is mechanical end, one can get 20 milliampere. Similarly, when the potentiometer at the other end, we have to make it is 0 milliampere. To get 0 milliampere is the only issue, because the potentiometer may not go one end, some voltage will be still left, and you may have a issue with that. So, to get a 0 adjustment, we have to do this circuit had to be modified. So, how to get 0 adjustment? So, span adjustment can be achieved by selecting a suitable value for suitable value of this suitable value for this resistance and then this one can achieve the span adjustment. So now we modify the circuit to include the zero adjustment. Now one can get the zero adjustment by adding another operation amplifier. For example, I can have one more potentiometer. Of course, if you want, I can also add another zener to this, and this is supposed to be connected through the voltage follower. Then our regular circuit. This two-wire system comes in, then we can have our potentiometer can be connected in this fashion. So this is the potentiometer, for example 5K, which determines the position of the mechanical system. Now for example, if the potentiometer is not going to one end, physically not going to one end, then one can adjust this as a 0. So we keep this as a 0 pot, and this is actually is what it is coming through the regulated voltage, and supply for this is actually coming directly from the so this is acting as a span pot. This is acting as a 0 pot. This is actually the position measuring potentiometer. So now for example, if it is not going to one end, one need not worry, because if the voltage is not equal to the supply voltage, then I can increase this by adjusting this. Of course, this in that case we have to have a provision that this goes little higher, so that it reaches this point. Now that also can be achieved by slightly feeding different voltage to this. That actually can be done by slightly modifying this part. Okay, what I do is I will have this. For example, I can have slightly higher voltage to this. So that I am able to get little higher voltage, and this voltage also can be increased a little higher, or even we can go down by moving it lowering this point. So we can now we have a flexibility to vary this voltage, so that we are able to adjust the 0 by even if this potentiometer is not going to the one physical end. So this gives a provision to adjust 0 and span. So we call this as a 0 pot. This is actually the span pot. This is the position pot actually. So by this method, one can, even if the potentiometer is not reaching full, for example, if this is 18 volt, we can go up to 17 point, this point goes to 18 minus 1 point to 16.8. So even if the even if there is zero current is there, then this will be sitting at 16.8, and since this voltage is little more than 16.8, even if there is a small gap is there and reaching the maximum end, one can easily move adjust this to lift this voltage higher. So that provision is possible. Of course, we have to limit the available voltage across this, so that can be achieved by adding a zener. So we need not give too much 1.2 volt can be the total variation that can be planned, or even 2.4 volt also can be planned depending on the selection of these resistance that we have planned. So, we had planned for 2.4 volt, we can retain this 2.4 volt and then do this. So, this way 0 and span adjustment can be provided for a 3-wire system. And now you could quickly understood that designing a 3-wire system is little complex than designing a 2-wire system. This is because we had to make sure that this voltage, the current flowing through this is actually maintain 0 and 20 according to the position of this. So, in practical terms, these issues to be considered if you want to maintain the current. Now, quickly you understood that designing this circuit looks little cumbersome, that we have to plan various voltages at various points. So, one can think of another simpler circuit than this to get this 3-wire system. That current transfer part will be like this. So, one can use this we call it is a current transmitter with ground side, ground end as lower potential, because we are now or other way around, we will say that this is a current transmitter without referring the reference to the supply, because in the, if you look at the earlier transmitter, current transmitter, we take supply as a reference point and then lowering this voltage, we are take the supply as a reference point and then we are lowering this to get the required current. So, this is supply reference current transmitter. Instead of that, we go for a ground reference current transmitter, then we will have slightly different problem, not the same problem, current transmitter with the ground reference, with the ground side reference. Now, that actually we can do the following general circuit, like for example, if I have this kind of current transmitter, and this can be supply, and then this can be our load, this goes back to ground, this is the reference resistance. What you do is, for example, I put equal values here, then normally what is done is I will give, for example, if the potentiometer voltage to be varied by the current, then I put the potentiometer here. This is the position potentiometer. Then to maintain the current constant, we go to this circuit. For example, if this is also 100K and this is also 100K, then assume this is common to V supply, and of course we can make it stable by adding a Z0 to this and have this, that is V regulated, for example V regulated, that is maybe 18 volt. This is one possible way of designing. In this, what we are trying is that we have these two these resistances which we have already discussed, for example R1, R2, R3, R4 are equal. Then if this is say V with respect to ground, then the current I actually is given by V divided by R. If provided this all four resistance are equal, if this all four are equal and this resistance is negligibly small, then what happens, that loading effect won't be there, and then this also small. In that case, this relation is true, the current that is flowing is actually depends on this V, and or other way around, when we increase the V, current will be increasing, decreasing, the current decreases. But then this assumption to be valid, if the assumption to be valid, then I have to make sure that I add up voltage for here as well as here. So if I modify the next level of circuit, looks like this, the what we can do is we will have so we have the reference voltage coming in. So I have 100k and the same 100k here. Then what I do is I will have the supply voltage. From the supply I have the xenon diode, then I position pot. So this is the position pot, this is the regulated supply, say 18 volt, and then I connect this as usual. Now here this one I feed through a voltage follower, so that this resistance has no effect on the working of the circuit. So this I will feed to this. Then here actually your 2-wire 3-wire system is actually connected to this back, and this is what the input will have a regulator here, and then given to the input. Now here this voltage again fed through a voltage follower. So we have this 100k and 100k is kept. So all four resistors are equal, but now we have added this, if you compare our earlier circuit, that now we have added these two voltage followers, because this voltage follower does not load this resistance. Similarly this voltage follower does not load this potentiometer. Because of that, now the accuracy of the circuit is improved, because the input impedance given by the voltage follower is very high. So first improvement is this, but still we have to worry that how will you make sure that these four resistors 1, 2, 3, 4 are equal, because if they are not equal, then the current will not be any more if they take this as V, and the current through this V I will be equal to V by R. The current I is equal to V by R is not strictly valid if these two are not equal, and the worst is if they are not equal, when this resistance changes, for example the current may be constant, the current may depend upon only this V by R. In first order approximation, that you have this V by R as the current, but then that current what is flowing here will vary little bit with this resistance, because the load resistance is not in your control. This is given to the customer, you may connect 600 ohm or even less. Now but not more than 600 ohm. When he connects a very small resistance here, when he connects a very small resistance, then 20 milliampere current flowing through that will produce only very small voltage. On the other extreme, when he puts 600 ohms, then 20 milliampere will produce a 12 volt here across this, and this point will be sitting at 12 volt, and the 12 volt has to be reproduced at this point. 12 volt will come as 12 volt at this point, and the 12 volt will make it 6 volt. But then if the whatever voltage that is coming here, that is also to be equally divided by off. For example, for no current, for 0 current, if this is 12, if this is a 0 volt, then this also will be 0 volt. Then if some whatever voltage extra is there, that will come by half, then if whatever voltage there, half of that will come here, and here whatever voltage there, that also half of that have to come. If this ratio is not equal to this ratio, then the difference is not correctly reproduced at this end. So we have to make sure that this ratio and this ratio are equal. So essentially calling that we call this ratio, they say R1 and R2, and this is a R3 and R4. So, if the circuit has work independent of this resistance value, that is the accuracy to be maintained, means then I have to make sure that the ratio R1 by R2 is exactly maintained as R3 by R4. Ideally speaking, 1:1 is okay, but nevertheless the ratio to be maintained. If the ratio is not maintained, then when the resistance changes, the current also will change. For example, if the user changes this resistance, then voltage developed across this will change. That voltage will produce a different error at this point and at this point, because this voltage is applied at this point by this ratio of this resistance. Whatever voltage is here, that is applied by the ratio of these two resistances. If this ratio and this ratio are not equal, the voltage at this point voltage at this point transferred to this point will be something, and voltage at this point transferred to this will be something else, and that will make that this voltage we call common mode voltage will have effect on the current. So, we have to make sure that this ratio is maintained constant. This is one of the major problem in this circuit. Otherwise, this circuit is much easier compared to the other circuit which we have discussed, because here one need not struggle with various voltages that we had faced, that problem we had faced in our earlier circuit, because if you see carefully, if this is 18 volt and even if this is close to 18, we have 1:2 ratio. So, this point never goes to 18, it is only half of that at the maximum. So, it will be always below 9. Similarly, whatever voltage that is coming here, that you have this is, if the resistance is 0, of course you will have close to 0, and assume the resistance is not 0, then this is also not 0, but even if it goes to 12 volt, then here what is coming is only 6 volt. So, as far as higher voltage is concerned, this op amp is safe. Of course, you may have a worry that what happens if the user puts 0 ohms, and if this goes to 0, then op amp will not work properly, because close to the ground reference point, single supply op amps do not work properly. So, this is the problem that we face. So, for that problem can be easily solved by adding a small resistance voluntarily from our side. So, I can add a small resistance, say 47 ohms or so that even the user grounds this, voltage at this point will not go to 0. So, that can be tackled. And similarly, the high voltage, say 12 volt is not a serious issue, it can go up to the maximum supply voltage easily, because even at 18 volt this goes only 9 volt, and this also goes only 9 volt. So, the circuit works properly even at 9 volt, because supply is at 18 volt. So, the 0 and supply voltage what we have faced there is not the issue in this circuit. So, if you look at the advantage of this circuit is that one, supply the op amp input voltages, the input voltage op amp is not at the supply potential. At the maximum they are only half the supply potential. At the maximum they are only at the maximum op amp input terminals are seeing input terminals see only half the supply voltage. This is one of the main advantage with this circuit, and then so this makes our working simpler. So this avoids too many complications that had come because of the supply, and then input, that is the position potentiometer. If you look at the position potentiometer, they are at the ground side. So the voltage can go down to 0. Now that we can solve, because if the potentiometer goes down to 0, then this voltage will go 0 and the op-amp may not work properly. This also can be solved by adding a resistance here, so that it doesn't go to 0. And if of course now soon we find that when this is not going 0, and if this is not going 0, if this is not going to 0, and this also will not go to 0, then output current also will not go to 0. That problem soon we will have. So that problem to be addressed, because we have to take that the op-amp is not will not go to 0. Then here of course this side the op-amp voltage now going to 0 can be addressed by adding a resistance here. Of course when the current is 0, then there won't be any voltage drop, and this also will force to go to 0. At that time this will not also work properly. So we had additional two issues now come in, that supply I side supply point problem is solved, but the ground side potential which is going to 0 is not solved. So the second issue is actual problem is at ground end the op-amps may see 0 potential at 0 current. Similarly, 0 current, solving by adding I call the resistors, for example R5 and R6, adding resistors R5 and R6, the problem is not completely solved. Adding resistors R5, R6, the problem is not solved. So not find a solution for this, but nevertheless we are better off compared to our earlier circuit. So we have to see how to resolve these issues. Of course one can resolve this issue by adding additional voltage at this point. For example, even this 0, that we can add some additional voltage to this, because if the problem comes when this is when it is not going to 0, then this also will not go to 0, but then we want for 0 current 0 volt. That can be achieved by only adding some additional voltage at this point. So we will not find a solution how to add additional voltage without disturbing the balance. Unless these issues are solved, this may not work for 0 and 20 milliampere. So now we have to explore this and see how to solve this ground side problem. Nevertheless, we are solve the major issue, that is supply related issue, that is op-amp terminals which are going very close to the supply voltage, that was been solved. So we see how to modify this circuit to take to solve this ground the ground potential, that is the op-amp going close to 0 potential. How to solve that we will see in the next class. Thank you.